So you want to pick a editor. Emacs is a good one. In fact, I'll show you really quick how I use Emacs. Let me start from scratch. And you can go away, you can go away. All of you can go away. Okay, so I'm using a Mac. I'll open up a terminal, and I'm going to go to where I have this data, which is in projects. This isn't gonna work for you because this is my own. Okay, so there it is, expression one. So I use Emacs, and this is what it looks like. In case you want to try it, it's what? No, not that one. Sorry, R. That's what happens when you don't spell right. Okay, so that's what Emacs looks like on a Mac. There's versions for Windows. There's versions from Unix. And let me just show you why it is that we want some kind of editor that is friendly to a programming language like R. So if I write a loop, you see it immediately puts color to it. You see that it's in color, so I can see that it's a loop, and it also tabs for me. So when I write a loop, I want things to be in a format that I can see it clearly that it is a loop, and now I can continue. Okay, so see how it's indented? That's a key feature of whatever editor you use. And here's another key feature, which if you don't have it, you might go crazy. Look at what happens when I close that curly bracket. Did you see that? Watch it again. It tells me that's the one you closed. Okay, because it's going to happen eventually. You're going to have like 8 parentheses going on. That will happen, and you need to see what you need to close. And here's another thing that is nice. Watch what happens if I close a parentheses. Look what it says on the bottom, down here. Unmatched parentheses. So it's saving me from making a mistake. Okay, so that is Emacs. It's a very nice editor. Again, it's kind of old. There's might be better things now, and I'll let you ask around of what other younger people are using. Okay, and today I'm going to try RStudio because it is much nicer to look at, especially in class. So I'm gonna kill this. And actually, see, this is kind of nice about Emacs. It doesn't assume I'm a super geek. It actually says, "Are you sure you want to kill it?" I guess a real editor would just kill it and not ask you. Okay, so let me open RStudio. It's free, and it is. Where did it go? There it is. Okay. There's RStudio. Okay, so here RStudio already has a little area for me to write in. This is where I'm going to write my script, and then I'm going to eventually save it. Right now it doesn't have a name. Here's R. Don't tell my geek friends that I'm still using 2.13, which is pretty old. Nobody tell Robert Gentleman that, or Casper. So this is R, and here you can see there's some stuff about where my files are, etc. And here, this is also a nice feature, are functions that I have defined in R. So if I define a function, it's going to show it to me here, so I know I have it and I can see what it does. All right, so let's get started right away. Before I start, I am going to see what happens if I can read this file from the internet. So I'm going to call it E for expression. Can you see? Do you guys prefer that I move this somewhere else? Let me see if you can see it. If I move it up, you can see it a little better. Can you see it better if I put it there? So we're going to be working here. And there might be a way to make the font bigger, but if I can't find it right away, I'm not going to do it. Preferences. Is there something there that looks like? Aha. What font should we use? Does 12? Let's go 14. Too big? People in the back. Can I use 12 or 14? 14? Okay. And now how do I tell that I'm done?
It's out of the window. You've got to make the window bigger.
No, I don't.
Stretch the window down again because it's getting cut out.
Ah, thank you. Oh, that's okay. Better now? Now move it up so everybody can see it. Okay. So here we are. This is the R prompt. Now I'm not going to write, I could write here, but I'm actually going to write here because I want to save it for later. And actually I'm going to change the name. Save as code 1. Okay, so now it's called code1.r. Okay, so the first thing I'm going to try is I'm going to try to read this off the internet instead of downloading and writing. And actually, RStudio does something nice. It actually doesn't even let me try to close the parentheses. It already did it for me. See how if I just make a parentheses, it closes it. Keeps me from making errors. Okay, let's find out what I think the web page is. HTTP rafalab jhsph.edu 688 expression CSV. Let's see if a miracle occurred and I typed that right. Whoop. And now I think I hit Command Enter and it'll automatically run it in R. See that? I don't have to cut and paste. I hit Command on an Apple, on a Mac. I hit Command Enter and it automatically brings me down here. Now did it execute it? What? Okay. Okay. Oh look, it worked. Okay, so I just read from the internet. I read a file. You could also download it and then write the path and read it in. If you have your own data, that's probably what you will be doing. Now, why did I do read CSV? Because I already know it's a CSV file. There are other readers. There's read table. There's read delim. How do we find out about all this? Well, one way is to read about read CSV and see if we learn more. So, very important thing to know in R. Very important. Everybody pay attention. Question mark, name of function, shows you help for that function. See how it came up over here on the right? So it says read table. What is that? Why is it saying read table if I ask for read CSV? It's because it's a family of functions that do similar things, and here are their names. Read tables 1, read CSV is another one, read CSV 2, read delim. They're all doing similar things. So now I can read how to use it. You can, and this goes on for a while. There's a lot of information there. It's good. It's all pretty useful. In this case, it's one of the most useful functions in R because it reads in data, reads in tables and the like. Okay, so now let's see what E is. Now, how do I find out what E is? If I type E and I hit enter, I'm not going to do that now because it could be trouble. If I hit enter, it's going to show me what's in that variable. And this I already know because I made this data set that it's 20,000 genes and 6 samples. So I don't want to hit enter because we're going to be seeing numbers for about 5 minutes. And so I'm not going to do that. So other things we can do is we could look at the first row. And this is how you look at the first row of a matrix or a data frame, which is I think is what this is. I'm not sure yet. So it's a square bracket is to subset a matrix or a matrix-like object. And 1 is going to give me the first row. If I want to see the first column, I say comma 1. But if I want to see the first row, I say 1 comma. Now this is already a really powerful scripting tool because if you want to do this in C, for example, you have to write a for loop and print every I comma 1. Here, if I hit enter, there it is. It just shows it to me. So by leaving the columns empty, it assumes I want them all. So that's the first row. So you can see, let's go up a little bit to see them all. The font is so big that. Okay, so look at the first row looks like some kind of ID. Then there's like what appears to be a sample name. This is an AFI U133 array. It's a Latin square experiment, replicate 1. And there's the value. That is the intensity that was read off the machine. This is gene level. Now, I actually don't want the first column to be an ID. I want this thing to be a numerical matrix so I can operate mathematically on it. So I want the first column of the data to become the row names and not an actual row. Now let's go. How can we do that? How do we find out? We don't email Rafa. We look at the help file. And then if that doesn't work, you Google. If that doesn't work, you ask a TA. And if that doesn't work, then maybe. If you're feeling lucky, you email me. No, just kidding. Okay. No, but I'm not kidding about looking through all the available help before you go ask questions, because you actually learn a lot by doing that. So let's just read the help file and see what it says. Okay, there it is. Read CSV. File, header, true, sep. Does anything there that helps? Not really. So let's actually look at read table, because many times what the help files do is they will these functions are all put together because they have common arguments. They have a lot of things in common, so they don't actually repeat them every time. So a lot of the arguments that are in this function are also in the other ones. So we go through this and look. See this one here? Row names. That looks promising. It's something about the row names. So how do we find out more about that argument? We go down and we look for it. File, header, sep, quote, down. Ah, there it is. A vector of row names. This can be a vector giving the actual row name, or a single number giving the column of the table which contains the row name. That's exactly what I want. So let's change my code. I'm going to come up here, change it. I'm going to say row. Was it with a dot? It was, right? Row dot names. And what do I want to say? Which column is it? Which one? The first one. Now let's try it. I keep doing that. Now I come down here and I hit enter. Is it thinking? Is my internet connection gone? Yeah, okay. It took a little bit, but it's here. Okay, now let's look at the first row. And now it is gone. The first row is no more. Instead, I have row names. So and actually there's a function called row names. You might as well learn it today. I'm just going to look at the first 10. There are the first 10 row names. Now that first column in the CSV file has been turned into the row names of this object E, and E is just numbers, which I like. I don't like letters or words. I like numbers. So now I'm just going to type other things you can do to find out what this is about. If I do dim E, dimensions, 22,000 genes, 6 samples. So how do I find out what genes they are? These are the IDs. Those are AFI IDs. They don't mean anything biologically. But if you Google that, you will probably find information on it. There are tools in Bioconductor that will map these to all kinds of information. And we will learn that later. Okay. So now what? Now what do we do? So it turns out that these, I know this because I created this data set. This particular data set has 3 samples from one condition and 3 samples from another. The first 3 are from condition 1, the second 3, 4 through 6, are from the second condition. So we can look for differentially expressed genes. So how do we do that? So I'm gonna do different manipulations here just so you can sort of get a sense for the types of things we can do. So what could we do? What is one thing I could do really quickly if I want to find genes that are different, or something really simple? Any ideas? Something really simple. The difference of what? Take the difference of?
Different levels.
Yeah, but so there's 3 and 3. So what difference do I take? You want to take all possible combinations?
No, just you group the two.
Group and do what with them? Take the
difference of the two averages.
The averages, thank you. That's what I was looking for. We're going to take the average. Now, look at the numbers. 1,968. In fact, let's look at the numbers. So here's one of the here's another great thing about R. This is why we use it, I think. I want to know the properties of these numbers. What do they look like? What does the first column look like? All I do is I type histogram of the first column, and I have a picture. You know how long it would take to do that in C? Or even Perl? I mean, those are great languages. They have their places in life. But it's not data analysis. So there it is. There's a lot of zeros or very small numbers, and there's a few really big numbers. Okay, you see that? This is a histogram. Most of the data is down here, 90% of the data, and then there's some really high number. So what did we learn last time that it's good to do when you have something like this? Huh? Transform it how? Log. Let's look at the same picture now with the log. Base 2 is my favorite. And look at how much nicer it looks. Now we can see something. There's a lot of 64s. There's a few 4s. There's very few tens of thousands. That's what the data looks like. So I'm going to go ahead and transform this data into logs. So I'm going to do it for the whole thing. So here's another great thing about R. You want to convert this thing into log? You just turn it like this. The whole thing, one shot. Turn the whole thing into the log. Now, in my first attempt, this wouldn't have worked because I had words. Remember the first time I read it in, I had a column of words. If I would have gotten an error saying I don't know what the log of 1,000_SAT is, right? I can't take logs of characters. That was one of the reasons I did it. So now I'm going to do that, and there it is. It's done. Now we have the log. And now I'm going to take the average. So let's see, how do we do that? So here's a very easy way, a nice function. It's super fast, and it's very popular in genomics. And it's the function rowMeans. And I want to do it for the first 3 rows. And I'm going to subtract them. Well, let's just do M1. That's the first mean. So I'm going to take the mean of each row for the first 3 samples. That's how easy it is. Hit enter. And it's done. That's how, and look how fast that was too. That was 20,000 means it just computed. Do I sound like an old person being impressed by how fast computers are? Okay, now M2. rowMeans. Now what? Now we want the other 3. That's 4 through 6. Whoops, sorry. Keep forgetting the command. Alright, now I'm done. Now I have the 2 means. So I have the means for condition 1 and I have the means for condition 2. There's one more thing I'm going to do because I want to go ahead and make an MA plot. I'm going to take the average of all 6 and call that A. Just like that. Now I can make a nice plot. Now I can make an MA plot. Plot. A M2 minus M1. There it is. Oh, this you can't do this. I will explain this later. I just want to make it look nice on the screen. I'll tell you how I did that later, but you guys aren't presenting in front of everybody, so you don't have to make it pretty. Okay, so there it is. M2 minus M1 against the average. Does that look familiar, that shape? Remember we saw it yesterday in lecture, Tuesday? That's where I got it from. It was actually this same data set. And is there any gene that maybe is differentially expressed? How about that one? That one is 1,000 times smaller in one sample versus the other. All right, so now, how do we find out what gene that is? Let me show you that. It's actually quite easy. It's the smallest one because it's negative. So I'm going to ask which min M2 minus M1. There it is. That gene, this gene here, whatever that is, 20754 underscore S underscore T, is the smallest, is that guy. And it is the it's the 7,061st row of our matrix. So that is already a nice, powerful thing we just did. We just screened the genome. We just screened all genes and found the biggest difference with just, what, 6 lines of code. We didn't need a couple of them.
So when you're adding function, because I saw maybe that's not only one, maybe a couple of them.
Maybe there's more of them.
Yeah.
Yeah.
So
We can see the first few. That's a little more advanced, but let's do it. You can order. I'm going to call it O. And now I can plot the row names of E for the first 10, the smallest 10. That's a little bit more advanced, but you can see how I did it. Let's do that one. Those are the top 10 negative ones. If I add an absolute value up here, I can just say ABS parentheses and I get the top 10 regardless of direction. But I have to do something else. Because I want them to go from, order goes from smallest to biggest, so I would have to change an argument called decreasing, make it true or false. So if you look at the help file for order, you'll see what I mean. Okay, so now there is something else we talked about last time. we said that this is the difference in mean, but how about biological replication? How about variance? Are those really big because they're big, or because they're in general big, or is it just that it's a gene that varies a lot? So for that, we have to compute the variance. And that is also pretty easy to do. So I'm going to call them SD1. Rowest. Oh, I need a package for this. Gene filter. Let me not do that. Too advanced. Library. So now here's one of the things that you're going to start learning about R. And this is now a bioconductor function that I'm going to load up. R is very small in what it does. It has the functionality is very limited when you just have the base package. It's limited compared to what it could do. The reason it's like that is because if we included all possible functionality, it would be massive and hard to maintain. So the approach that R has taken,
You have to show how to install that.
I'll do that. But yeah, I'll do that. So I've been asked to show how to install Bioconductor packages. All right. So So the approach that is taken by R is that it has a base functionality, and if you want to add things, you are on your own in having to add these libraries. But they make it quite easy. There's a function called install.packages that will automatically download them, and there's another function called BioCLite. Is that what I have to do? I have to go on the internet and get it. Okay. Is there not a pull down here where I can install? Tools, install packages. Hey, look at that. Can I rant about something? This should be ordered by population, not alphabetical. Because I'm sure there's more people in the U.S. using R.
Automatically, based on your IP address.
There you go.
I mean, most people actually do that already. I don't know why R doesn't.
You know what? If you write a complaint to the R news group, you would be my hero. But I warn you, you will be flamed very hard, especially by the Brits. Okay, so Pennsylvania's close.
You go to the one in Maryland.
Oh, there's Maryland?
Yeah, National Cancer Institute.
Oh, yeah, but sometimes Maryland's farther.
Farther away than Pennsylvania.
Sometimes. Okay, repository. Okay, CRAN is the main repository for R, but what? No bioconductor? Huh? Where? Alright, we're gonna do this later. But there should be bioconductor in the pull down menu, I think. But we can have it be added there. Now, how do you install it from the command line? You can do that too. There is a piece of code that you can actually go and get, but I know it by heart. I've used it a lot. I still have trouble spelling bioconductor. And it's bioclite.r. So now I'm actually this source. So read.csv is for reading data. Source is actually to run a script. So if you have a script that is a file, you can source it in and it'll automatically run it. So this is a script that is on the web. So we just source it, and now it has a new function that wasn't there before, called bioclite. And now I can say bioclite. Is that right? And then I'm not going to do it because I already have it, gene filter. And then it'll install it automatically. It should. It might. Which one? What do you want?
The console.
This one, right?
Yeah, just so we can see. There we go.
And you can look at the arguments of bioclite and see what else you can do. So I should teach you that, I guess. Here's
Actually, if you don't give it an argument, it still is a nice.
A bunch of stuff.
Yeah.
So yeah, but in this room we might not want to do that. So there's a lot of us. Yeah. Okay, but let me show you this. Args, bioclite, or any function shows you the arguments that it has. This one just has 2. So yeah, so if you want to try it, you can do that. But in the meantime, if you can't do it, just follow along for a little bit and I'll put the script up so people can you all can try it later. So now the library is now installed, and I have a whole new set of functions. For example, a function called rowSDs that I can use to get the standard deviations for every gene. And I can do it for the other ones too. Okay, there we go. Oh, give it a different name. That's it. Now we're done. Okay, now, so now I have the standard deviations, and I can form a t-test. There's a faster way to do this, by the way. I'm not torturing you guys because there's actually a function called rowTtest that does that automatically. But I do want to go through the motion so you can see how you can construct these things. So what is a t-test that we learned to work with last time? It's m2 minus m1 divided by the square root of s1 squared divided by 3 plus s2 squared divided by 3. Right? That was a formula we learned last time. Did I do something wrong? No. There it is. That's the t-test. Okay, now let's look at that. So we can make a histogram of the t-test. Ooh, there's some really big ones. Here's something you can add to this. N class gives you more bins. Okay, so here, this is the t-test. So you can see there's a nice like t-distributed thing down here. That's probably between -5 and 5. Those are all the false positives, of the ones that aren't real. And then you have some really big other things. Okay, next step. Let's get a p-value. Yeah, go ahead. N class, look at the bins. See how there's more little bins in the histogram? Let me show you again. Look at the difference. So here's just, this looks like it's like 5 bins and now 100 bins. But there's some really, really big outliers that are way out here and way out there. Okay, now to get a p-value, I'm going to use the function pt, and I'm going to get the absolute value of the t-test because I want it to be two-sided. So I'm going to ask, what is the chance of seeing a t-test that big? And I have to give it the degrees of freedom, which I think is 4. I haven't explained that in too much detail here. I will eventually. That should give us p-values, I hope. And it's 1 minus that. Oh, what did I do? Where did it go? Uh-oh. Dude. Okay. Okay. Nope, p-val. Oh, I have to multiply by 2. I forgot about that a little bit. Okay, so for those that have been doing their homework with learning some statistics, that gives me the chance of seeing something bigger bigger than that than the observed value under the null hypothesis that this is a t-distributed statistic. But we're doing a two-sided test, so we need to be able to go both ways. Bigger extreme on the right side, extreme on the other. So we have to multiply this whole thing by 2. And now I have histogram of the p-values. And this is actually a good sign. P-values are supposed under the null, when nothing is interesting, when no gene is differentially expressed, it should look like a uniform distribution. And that's roughly what we're seeing. There's maybe a little bit a little bit of height here, but that's good because that means there's maybe a few genes that are differentially expressed. But if nothing's differentially expressed, the thing should look uniform. And there it is. It looks pretty uniform. Okay, but now what? What else can we do? Yeah, question?
One side passing is by default.
Huh?
One way passing is by default.
One-sided? No, I would say two-sided is the default. Should be.
In PT, it does one side.
Oh, PT. What does PT do? That's the question. PT is not really computing a p-value. PT is for a given number. It's computing the probability that the t statistic is smaller than that value. So if it's 5, you're going to get back almost 1. Let me just show you. So PT of 0, what is that? What should that be? Statisticians. Huh? Half, right? Half of the things are smaller than 0. How about if I put -5? What is that going to be? Practically 0, right? How about 5? What should be 1 minus that? Okay, so you see this is the probability of a t distributed number with 4 degrees of freedom. The probability that's smaller than 5 is 996. So so the probability that's bigger than 5 is 0.03, and then I have to double that because I want two-sided. That's how I got my p-value. Okay, man, I want to make the volcano plot before we have to end. It's almost 3. That was the last thing I wanted to do. So what is a volcano plot? The volcano plot is M2 minus M1, the observed difference, and minus log 10 of the p-value. Okay, that should make us a volcano plot. And while we're here, I'm going to just show you one little trick. You can put a title on it. There's our volcano plot. And here's, I'm also going to show you how to make labels, X label. So how do we learn all these things? You want to do, this is something that everybody should do if you're going to use R. Type help, question mark, par. And you should read the whole thing. And you will learn a lot about making pictures in R. This is long, but it's super useful. See how long that is? Huh? Okay, so let me make the volcano plot again, and I'll add the label. So what's the X label? Effect size. And the Y label, is minus log 10 p-value. Okay. So now the axes have names. Alright, there's a volcano plot. So what do you think? Are those really differentially expressed? The p-value is like 1 in a million. The effect size is 1,000 times smaller. Right? Those are looking good. That one's looking pretty good. But now here, look at these guys. These guys have pretty big effect sizes. Fold changes of like 8. But the p-value is not small. So that's probably those are probably not real. And then you have these other things here. We're gonna do more of this next time. This data set, by the way, is a spiking experiment. 16 genes are differentially expressed and the rest aren't by design. So can you tell what are the 16s from this picture? You can tell 1, 2, 3, 4, 5, 6. Then what? So one of the things we're gonna learn in this class is how pre-processing makes this much nicer, and how statistics other than the Ttest make this nicer. So now that we've learned all about the Ttest, if you have 3 against 3, do not do a t-statistic. It's not a good idea with microarrays. This mess, it kind of shows us that we shouldn't. This is a spiking experiment. There's no biological replicates. It's all technical, so it should be really clean. We should be able to see the 16 spikings clearly. We really only see 3 or maybe 5 clearly. Why is that so bad? 1, pre-processing is bad. 2, the t-statistic is not the most powerful approach here. We will learn how to pre-process better. We will learn better approaches to defining statistically differentially expressed genes. Okay? Okay. Go ahead. What's the question?